Welcome back to AP Chemistry, everybody. This is Unit 13 and Section 2. We looked at different types of rate laws, and now this section is all about the integrated rate law. Okay, so just a quick review. We did a differential rate law that was taking a look at the concentration versus rate, and now we're taking a look at the integrated rate law, where the differential rate law expresses rate as a function of reaction concentration and an instant in time. Okay, so it's a little bit different where we see a concentration this time versus when we see versus rate. Okay, so the integrated rate expresses reactants and concentration as a function of time. So once again, we see a table of things, and we see that there are different orders of reactions that are going to be going here. And I know this is a lot to process here. There are different types because we're looking at time in here. A zero order, first order, and second order is what we're looking at. So if we know it is a zero order reaction, then our rate equals K. If we know it's a first order, that's going to be our rate equals K times the concentration of the reactant there. And then if it's a second order, we're going to square it. So it's to the 0 power, to a 1 power, to a 2 power. Okay, that's all we're doing here. The reason you don't see an A is because it's to the 0 power. Now the integrated rate law is, that's what this is all about, is taking a look at time. Okay, and so we're going to be seeing the K value, my concentration equals the negative K times time, plus whatever that concentration was, add 0. I take a look if it's a first order, the natural log equals the negative K value times time plus the natural log at 0. And then I have 1 over if it's a second order. Okay, so we just have to remember which equation for the integrated rate law we use. Now, the key to all of this is the plot we needed to give a straight line. We were going to be taking a look at a straight line, and that's how we know we can see the graph of it, and we can see what order this is going to be. The relationship is going to be a negative K, and a positive K. Okay, and so the half-life then is what we're going to be calculating from that. We just simply take that initial concentration divided by 2K, 0.693 divided by K, or 1 over K to the to that 0 instant. So there's just a lot of stuff we are doing in there, and our graphs, if we take a look at this, the natural log is going to be the concentration at the start towards any time in there times K times T, and you'll notice this is graphing out those different slopes. Okay, so we can see those, and you basically just compare it to the graphs, guys. I know it's a lot to process, but the products are going to be either a first 0 first or second order in there. Okay, so let's take a look at what this is doing throughout, and remember that we have the equation. We see that polonium is going to decay to this equation. They are telling us in this first problem, they are telling us that it's going to be decaying the first order. They're telling us that it is a first order decay. Okay, so that's going to be a key to this as we are solving the problem. Okay, if we begin with 5.28 grams sample of pure radon, then we want to know how much time is left over. So we have our time of 1.96 days. Okay, if we know it's a first order, we take the natural log of that 5.28 grams. Okay, this is a natural log, and we're going to be taking that of my concentration. Okay, that's going to equal my 1.96 days, but we know the decay rate of a 0.181 per day, and we see that it's going for 1.96 days. Okay, so if I take a look at this, just multiplying that out to speed things up, that's a 0.355. And so if I take the natural log of this and do all the math with there, I end up with my concentration at the end of the time being 3.69 grams. Okay, so that's all we have to do. Now, what if we had 3.82 days? Well, that changes this part, doesn't it? And so I'd take the natural log of my 5.28, that was my start, and we want to know the concentration at the end. That's going to equal 0.181 grams per day. And this time I have 3.82 days. So these are pretty easy. We just have my concentration at the end of things is going to be 2.64 grams. Okay, that's at the end of 3.82 days. Cool. So that's pretty straightforward given that particular type of problem. Now, we can also go through and we say, all right, and there's the equation, if you guys were wondering, there's the equation for the first order, okay? Now, let's take a look. If we know the half-life is 20 minutes, we're going to be calculating the rate constant, if we don't know that. And then we can go through and see with the percentage. So let's figure it out. If we don't know our rate constant, let's go ahead and figure this part out. Now, again, they're telling me it's a first order reaction, and that's key for us, okay? So we know that in part A, that the half-life is going to be, that ends up being 0.693 times times my constant, okay? And so the 0.693 comes from my seconds, and then I plug in my value of time, that's 20 minutes, equals 0.693 over K, and so my K ends up being 0.0347. Okay, and so that's basically just plugging values in, and I find that a certain one in there is going to be following there. All right, so all I have to do with these is just find those values. Now, if we found that the half-life was the rate constant for that reaction, and so I would then go through and say, okay, now that I know this, how much time is required for it to be within 75% completion? Well, remember that the natural log of my initial over my my ending is going to be a function of my K versus my time. So if I find that my initial was, say, 100 over 25, that's going to be equal to my 0.0347. That was the rate that I found. Or sorry, that was the constant that I found. And I'm going to solve for t. My t then ends up being 40 minutes. Okay, so how did I get that 75%? Where did I get my numbers? Well, 100 divided by 25 gives me 75. Okay, so that's my 75% complete. I had 25% remaining. You could plug in any numbers in there, but if I started with a 100-gram sample, 75% completed, I'd only have 25 grams left. Okay, so pretty straightforward with that. It seems like we're missing some information, but we could figure out based off of there how we would go. Okay, now we take a look at copper. It decays by first order kinetics, and we see that it has a half-life of 12.8 days. Okay, what would be this value in K in something over seconds? Okay, so that's just going to be our half-life, isn't it? And so I find that my time would be the 0.6931 K. Okay, and so I end up with that value ending up being, I'm just going to plug in some numbers here. Lost my spot. Okay, so I have 12.8 days equals my 0.6931 K. Okay, and so my K ends up being 0.054 per day. Okay, but they want it in seconds, don't they? Well, then I just do some transformations. So this is 0.054 grams per day. 1 day is 24 hours, and 1 hour is 60 seconds, or sorry, 60 minutes, and then 1 minute is 60 seconds. Okay, so I end up with 6.2 times 10 to the -7th grams per second. Okay, so just watch out for your units there. This is just a dimensional analysis problem. Okay, now taking a look at another an extension of this. If we had 28 milligrams of this, how many decays would be produced in the first second? Now remember, we had in this we had 6.2 times 10 to the -7th grams per second, didn't we? Well, if we got that, I had 0.028 grams. Okay, or sorry, that's milligrams. So that equals, let's see, and we want to know how many decays would be in the first second. So that's sorry, this is going to be 0.028 grams. And so if I have 0.028 grams, that's going to be 64 grams per mole. And then I have 1 mole is 6.02 times 10 to the 23rd particles. Again, we don't want to know how much is left over. We want to know how many decays. Okay, so I just take a look at how many particles in there, and so I do the math. I end up with 1.65 times 10 to the 14th decays or particles lost per second. Okay, so just use Avogadro's number from the moles. All right, next problem we're going to be taking a look at is taking a sample of copper 64, and we measure the radioactivity. We find that the experiment to do in mind, the radioactivity cannot go below 3% of the initial value. Okay, and so we see that this is going, and we want to know how long she can do the experiment. Okay, so remember, 3%. So we're going to take the natural log. What is 3%? Well, we have a sample that's 100, and it can't go below 3. That's going to equal 6.27 times 10 to the negative 7 decays per second times time. Okay, we're going to multiply this by time. So my time ends up being 5,592,596 seconds. Okay, so that's what we've got. Now, if we took a look at that in terms of days, well, we'd have the natural log of 100 over 3. Okay, that's 3%. That's going to be 0.054 per day times time. My time would be 64.9 days. Okay, so that's how long she could do that. So we take a look at the values of that and just plug them in. Okay, nothing too bad for those types of calculations. Get this to cooperate. All right, so we're going to be taking a look at the next one. This is kind of a different approach. I'm going to show you the answer in the end. So we're going to see butadiene is going to react to form its dimer according to the following equation. And we see the values here. And so we want to know the reaction order, and we want to know the value of the rate constant for the reaction, and we want to know the half-life for this reaction. And so just taking a look at these values and everything, I've got the answer actually posted here. To figure out the first or second order, we want to see whether the plot of this versus time is a straight line, or if it's going to be something else going on. The data necessary to make the plot are as follows. And so what we see with that table, the resulting plots are shown below. And since we see that we're plotting it out, I can see, oh, which one gives me the straight line? It's a second order if you get a straight line. And so we would know that the slope of the line can be expressed as you see in the equation. Okay, so that's not too bad. And so basically you just kind of answer the question by plotting the data out. So it takes a little bit of time to do this, but all you need to do is plot the data. Now, we can take a look also for the second part of this. If it's a second order reaction, a plot of 1 over the concentration versus time produces a straight line of the slope of K. In terms of the standard equation for that straight line, y equals mx plus b, then we have y equals 1 over that concentration and x equals t. Thus, the slope of the line can be found on the screen. So using the plot points at t equals 0 and t equals 6,200 at the end, you can find your rate constant for the reaction. And so your slope is going to be the 481 from your data minus 100, and your change in your 62 versus when you started, that will be this, and you'll end up with 6.14 times 10 to the negative second, okay? That will give you your value for that one. Now, the expression of the half-life then, if we plug those values in, in this case, K equals, from part 2, we just carry that over, 6.14 times 10 to the negative second. We see our values from there, the concentration at time, and so we end up with the time ending up being 1.63 times 10 to the third. Okay, so you just kind of look through those things. I wanted you to see kind of how we solve those problems, and you've got a way to coach through it, but it's basically the same thing I was showing you before. All right, so you've got enough to do section 2, and I wish you luck on that portion.